Donc, on va passer à la présentation suivante. Donc, c'est Mohammad Abbas. Il va nous présenter son travail sur Mesoscopic modeling of the behavior of interfaces between reinforcing steel and concrete.
Bonjour. So I will be presenting in English today. I hope everything will be clear. So my name is Mohammad Abbas. I'm starting my second year PhD thesis, which is related to the mesoscopic modeling of the behavioral interfaces between reinforcing steel and concrete. It is directed by Benoit Bary from SSR LECPA and Ludovic from SOMT LMDS. So RC structures have functions that go beyond their simple resistance, and as an example is a containment building that contains nuclear power plants. Interspecies cracking has a direct impact on the transfer properties that control the leakage rate. The bond between steel and concrete which plays an essential role in determining the structural performance of the RC structures and the crack properties. This steel-concrete interface is very complicated due to the presence of various phenomena at the region, such as corrosion, slip separation, and air voids, and the presence of different materials like fine aggregates, coarse aggregates, and the cement material itself. Studies on the previous studies were done on the steel-concrete interface. Macroscopic studies were done in LMDS. By taking the concrete as one homogeneous material. On the contrary, nanoscale simply takes the concrete as made out of atoms, which is not studied previously. And macro level takes divide concrete into 4 different phases: air void, fine aggregates, coarse aggregates, and the cement material. And what I'm studying right now is the mesoscopic scale, which divides the homogeneous concrete into 2-phase heterogeneous material made up of the mortar and of the coarse aggregate itself. However, it's difficult to use the mesoscopic scale to model huge structures. That's why it can be used to calibrate the macroscopic interface laws. Pull-out tests are usually used to study the steel-concrete interface. It's simply pulling a steel bar outside of a concrete sample, and the loading is increased until there's a failure of adhesion between the steel bar and the concrete. And the relation between the applied force and the freehand displacement is plotted and measured, and it's considered the macroscopic behavior of the specimen. The objective of my thesis is to model RC samples at the mesoscopic scale, then run pull-out test simulations on these samples in order to eventually try to improve the calibration of the macroscopic models in LMDS. The mesoscopic scale, which I'm modeling, takes into consideration a detailed geometry of the steel bar. Previously, smooth bars were used, or the ribs have rectangular sections. Ribs usually control the cracking at the interface, so they are essential for modeling. Second thing is to include coarse aggregates. Most of the coarse aggregates were neglected in the macroscopic scale, and simplified geometries were used in other mesoscopic studies, such as spheres or circles, depending on the type of modeling. Those aggregates affect the crack directions in the concrete, so they are important to include. A 3D study, because most of the 2D studies use the complex shapes, however, previous 3D studies used the simple shapes, so we are trying to combine the flows and to bypass them. Pull-out test is simply used to study the steel-concrete interface, but the aim is to apply it to any RC or PC element, not this specific one. Finite element modeling used for solid structures, and because of the complex geometry and because it usually takes less time compared to discrete element modeling. So in previous studies, the different approaches were used. 3D discrete element rigid body spring model, where the concrete was modeled as a homogeneous material. So it's a combination of a mesoscopic, macroscopic kind of modeling, although it took a kind of complex shapes. Lattice model was used previously in both DM and FEM, but mainly 2D studies take into account coarse aggregates, circular aggregates. An interesting approach for modeling a sample was also in this kind of study, which used which was aimed to study corrosion, and where concrete aggregates were considered as complex polyhedrons, and the whole sample was divided into 3 different materials. So in here, starting from that point, I'm going to use to model using a model built in LECPA and Al-Jalas to make a realistic sample generation, and then mesh this sample, all this using Salome. Then to use Cast3M to run linear simulations in order to using elastic models just to study the functionality of the model itself. First, and using a linear spring model for identical stiffness and star, then variation of the stiffnesses. After that, nonlinear simulations will be run first using a simple, using classical Mazar's model where I stand right now. And then after that, we're going to design a new behavioral steel concrete interface, modify, compare, until finally reaching the calibration of the macroscopic models. So the script used for modeling was developed in the MDS LGS called Combus. It was used in previous studies in LECPA, for example. It uses Salome, as I mentioned before. The cubic sample is a build. It's made up of 3 different materials: mortar, which is the biggest part of the volume, coarse aggregates modeled as a polyhedrons, and the steel bar, which will model take into account the real shape of the ribs themselves. As a start, the herringbone shape was chosen. The steel bar was modeled based on previous pull-out tests, and where the adhesive part of the bar contains ribs, while the non-adhesive part, or the part which is usually covered by plastic sleeve or it's surrounded by a gap, is a smooth bar. Different pull-out test shapes were used previously, so we modeled different shapes in order to compare the results with experimental previous results. The rib is a trapezoidal, had a trapezoidal section, isosceles trapezoid with an angle of 60 degrees. This can be modified up to 45 degrees to check the effect of the rib angle on the spreading of the damage. The second thing is to choose to model the aggregates. So they were convex polyhedrons. They were initially only particles. Each particle was rescaled randomly, which leads finally to a unique particle, a large number of unique particles. Each one cannot be similar to another. These particles will then spread surrounding the steel bar in the sample, and after which the mortar filled the spaces. The sample after that was ready to be meshed using Salome. A regular mesh was taken into account, and using linear tetrahedral elements. Different samples were used. For example, this kind of sample was a finest sample, although it's 1/8 the volume of this sample, but it contains a large number of elements. It's mainly used for damage and to check the cracks near the steel interface, because the fine mesh, which fine mesh study controls shapes at this point. After that, linear simulations were performed using Cast3M. Steel bar mortar aggregates were all assigned elastic behavior, steel motor interface, and linear spring model. The boundary conditions were the same as the pull-out tests, imposing a displacement at one of the surfaces of the steel bar, blocking the surrounding mortar in the same direction of the pulling force, and 3 kind of points were blocked in the 2 other directions in order to prevent any indeterminacies during the measurements in Cast3M, calculation Cast3M. The elastic spring model, linear model, was chosen for simple checking of the functionality of the problem. It will be improved certainly in the near future. Here with normal stiffness, technically resembles the resistance in the normal direction, which can be seen on the sides of the ribs, while the shear stiffness resembles the resistance in the directions parallel to the surfaces, so it's technically everywhere at the bar. For the sake of comparison, sample AS was also modeled, taking into account the same properties of a previous sample, but using a smooth bar, fully smooth bar instead of a ribbed bar, with the same properties, with same adhesive length in the central part, non-adhesive surrounding, same placement, and the same inner diameter. After that, identical stiffnesses were assigned for the linear spring model. The first simulation, 10^12 was used for both cases, and then 12^15, and it showed which was expected that 15 was simply higher resistance, and that stresses are higher at the in front of the ribs in the direction of the pulling force in the mortar, technically, which is displacement. After that, stiffnesses were varied in order to study in general the effect of the ribs. First, Kn is taken equal to 1015 is fixed, while Ks was varied from one simulation to another, and the free end displacement was plotted as a function of Ks, and also the applied force by the free end displacement was plotted as a function of Ks. You can see that for low Ks, values of Ks, the ribs prevented the bar technically from slipping. The post displacement is 2.05 millimeter, you can see. While for the smooth bar was technically no resistance at all for these certain values. So the only thing which played a role in here was the ribs. However, for high values of Ks, the ribs played no role at all in the slipping phenomena. The smooth bar and the ribbed bar had the same behavior in general. The only difference was that the smooth bar needs a slightly lower force in order to pull it out. It's very small compared to the ribbed bar. After that, the Kn was varied, while Ks was fixed at a certain value. The same kind of plottings were done using, as I said, the sample A using a ribbed part in the middle, non-adhesive parts, and this is adhesive part in the middle is smooth. For a in here we can see that there's a difference compared to the previous case. There is a similar behavior for both parts, for low and for high, which means they are as close in both cases in here. And there is no wide difference in general when the Ks is changed compared to the previous case. But an interesting thing to view is that Kn has a certain effect on the smooth bar, which smooth bar, as you see, the Ks again gain some strength with the increase of Kn, although it contains technically no ribs at all. So that possibly can be due to the retraction leading to compressive stresses, but this will be studied more deeply in the future, especially using different values Ks to check the effect in general. After that, nonlinear simulations were performed using classical Mazar's model, which is a standard motor. This linear spring model was still used for the steel concrete interface. The first try was a non-regularized formulation, and now using sample B, which have a different kind of shape, sample of steel bar. Parameters assigned were the one default that Cast3M as a start, but they should certainly be calibrated, especially the AT value. Here we can see of this sample the ribs, the damage here in post displacement is only 0.0125, which is still very small compared to the size of the sample. We are still in the elastic region for this in this simulation by plotting the force, applied force, and the post displacement. You can see that the rib, some cracks started initiating behind the ribs, and then as mentioned that the ribs would show them there will be some cracking surrounding the ribs. Due to the size of this sample and due to some computational time which will take, this sample will be another sample, smaller sample, which had a finer mesh was used. In this case, regularization was used by taking exponential evolution. Ks and Kn still fixed at K at 1015, but it will be certainly varied to check the effectivity, which was already done in some places. The simulation performed a smaller sample, as we mentioned. And still we are still in the elastic region in the total behavior, which means that we still need to impose a higher displacement. And we can see that there are inclined cracks starting from behind the ribs, which is the expected behavior in this case. And there is one at each rib, and also in some cases when the crack just faces an aggregate, which is the crack faces the aggregate, the crack will start surrounding the aggregate itself with the increase in the displacement, which is an important point in this kind of studies. In order to run more simulation, the aim now is to increase it. The imposed displacement is running right now. The damage should, of course, reach the rear 5 face of the mortar, and the inclined cracks are technically increasing in length with the increase of the displacement until reaching a total failure, which we are aiming to. Additional thing to do is the usage of possibly exploration of the usage of a phase field approach to describe the regularized damage. And of course, to study the effect of loading and confining the sample outside, which was studied previously in the macroscopic studies in order to compare the effect on the shapes of the cracking and of the global behavior. Another possible thing is to draw the distribution of the aggregates near the steel bar in a gradual way, predict some kind of aggregates, certain size near the steel bar, another size away, or dividing the bar in different regions, like a kind of homogeneous region out far from the bar and kind of two-phase heterogeneous concrete region, which will be studied. Of course, studying the effect of reducing the mesh, which is important, especially in the kind of non-linear simulations, because the mesh controls the shape of the bar. Using a higher mesh, we cannot see this kind of cracking. They will be invisible because due to the large size of these elements. Of also studying the effect of reducing the smallest aggregate size. So just lowering the limit of the fine coarse aggregate between the fine coarse aggregate. Then we did the effect of the shape of the aggregates themselves, which are used convex polyhedrons. There are cases of the concave polyhedrons and of course some kind of spheres to see the difference. More to add is a spiral bar, which will be modeled. It's not exactly this shape, but it's a very spiral bar because it's most common, and the comparison will be done with this kind of ribs, which have different section, almost different kind of inclination. They'll be introducing a creep and shrinkage to the model, which also, and of course the assigning a model of mortar steel, which is the most important at this point. We're thinking of a cohesive fusion model, the start, or the contact friction model, but more deep study on these two will be done. After that, we'll be checking the effect of adding an aggregate mortar interface, which was considered perfect during this calculation, to check the effect on the general behavior between a simulation that have no coarse aggregate mortar interface and having aggregate mortar interface. After that, of course, the main objective will be eventually is developing a tool to calibrate the macroscopic models. All this should be done in the coming 2 years for PhD. Merci de votre attention.
Thank you for your presentation. Est-ce que quelqu'un a des questions? Je peux prendre la parole. No.
Ouais. Bonjour. Sorry. I have a small question about your presentation. My name is George Nas from RSN. In this scale, I think so it's very important to introduce the effect of shrinkage of concrete, because the phenomenon is very important to opening cracks in the concrete and the steel together. What's your opinion about this?
Yes, the phenomenon of creep and shrinkage will be indeed introduced to the model because it's very important for the surrounding concrete, along with the mortar steel interface. So these are kind of related to each other. The creep and shrinkage plays an important role in concrete and mortar. So it's introducing this is one of the main goals right now, following this, along with adding a mortar steel interface to kind of related, because they technically play an important role.
Sorry, for this, you can't working in the global model. We need this approach with, for example, introduce the gradient of humidity in your concrete. This is a problem for that physics problem, and because it introduces the incompatibility of strength between your aggregate and your bed, etc.
between aggregate and the mortar?
Yes.
Yes, I mean.
No, yes, because this new, comment s'appelle, the interface, yes, the interface between aggregate and mortar is very parameter, and especially the humidity,
Yes.
and etc.
Yes, yes. As mentioned here, the perspective of the aggregate motor interface will be studied now. We're taking into account it's a perfect, so we are just neglecting some of this effect. But creep, shrinkage, also the thermal effects in general, will be added to the kind of model just after finishing the first steps of studying the damage. Without this kind of effect, then the aggregate motor interface will be assigned a certain behavior to check the effect of creep, shrinkage, along with the thermal effects, surrounding effects, because as I mentioned, it's the leakage phenomena in general and the cracking is studied, so kind of humidity, thermal effects are important also in the bulk sample.
Okay.
I'm gonna ask a question. So you've shown in the first slides the experience. Will you do some comparison? No need to go there. But will you do some kind of comparison between the experience results and the numerical results to see like how off we are now with the elastic perfect mortar contact between
Yes.
between, yes. Do you
Yes,
have
we already
see the before going to more complicated
yes.
modeling, like to see now how off we are from the real result.
Okay. Yes, I mean we already have some experimental results that's simply done mainly in LMDS lab on these samples. So we're trying to compare the results with experimental results. In case of the elastic, the important thing is to compare is the slope. So the slope of the applied force versus the free end displacement. We are already, which is the study we are trying to do here. So, the slope is trying to compare it with the experimental slope, and the case of perfect contact between particles to check what kind of values are values which can represent more or less experimental. After which more study will be done on this in case of a linear simulation, considering that the curves in linear simulation are simply straight lines, cannot be compared only except in the first part to the experimental results. That's why that damage is added, and also in damage some kind of KSKN or the linear model is also used, which can make is able to compare this kind of behavior to the experimental directly from comparing the elastic region and comparing the peak and everything below, based on these values, from which we can see how far or how close we are to the experimental results using this kind of formulation before proceeding. Which is, so yes, it's one of the points we are doing right now.
Okay, if there's no other question, we're gonna move on to the next.
Yes. Sorry, small question about how many time using this computation.
Okay, so it depends on the sample. So, for example, this sample which I just replaced by another one, is just to add to zero for this very, very small kind of, it'll take like more than 24 hours, which is simply nothing, because we are still in the start of the elastic region, this kind of sample. That's why I changed to this kind of sample using the same behavior. This takes about 35 hours, but we are still also in the elastic region because of the huge number of elements. We have like 2 million elements in this very small sample. This is an 8 centimeter sample. It's funny mesh. So yes, it is time consuming, but we're trying to get results. We're trying to take into consideration all the recommendations of pull-out tests, the size, so that these samples can be compared with experimental results. Yeah, it's not time consuming, especially with large irregularities inside the sample.
And about size of your matrix in Cast3M.
The size?
Yes, because when beginning the computation in Cast3M, you have the size of your matrix.
Yeah, I mean, the mortar is technically, I mean, the size you can see in example here, it's number of elements.
No, it's size, informatic size.
I'm not sure, check.
In your computation.
It's based on, you know, the same, it's in the mortar.
Okay, no answer.
Okay, check. That should be 2.5. I think the size of the matrix itself.
Yes, in your
yes, I understood the matrix for solving the nonlinear tables. I didn't check the value exactly what's.
Yes.
No.
Do Cast3M you send you the value of your size?
Yes, yes. I mean, I don't have the value right now in here, but
billion,
but
world, etc.
yes, I mean, I don't have the value right now in here, but I understood what you mean. The size of the matrix which is used in calculation in Cast3M. But I don't have the value right here. But from what I know, it takes a lot of time just between initiation of the Abbas situation and of the first simulation just to put up this matrix. I didn't take into account the value, but mainly based on the number of elements, I guess, in general of the sample. That's why I decreased it, but it's still taking a lot of time. That's why I don't have exact answer right now.
Okay, thank you.
Thank you.
Thank you very much, Mohammed.